right on two. Now we're dealing with not the atomic orbital theory or the valence bond theory. We're actually going to deal with the molecular orbital, MO theory. And so this is actually a fairly new theory, I'd say, developed in the last 3 decades. And so this is something the College Board wants us to know because it helps us to explain another exception to the Vesper theory. Knowing that the Vesper theory helps us explain molecular geometry, the valence electron bond theory is going to be more helping us with the electron domains, electron group geometry, and double and triple bonds. The molecular orbital theory's purpose is to help explain resonance. And so we know that resonance is an overlap or a superposition of multiple valid Lewis structures. And so the one I was mentioning in our last slide that we just went through was benzene. And so benzene, you know, looks like this. Or as some of you might draw it, like this. Or as some of you might draw it, you can draw it with a dashed line between to say that the second bond is able to be anywhere, but we know that it's not really a second or a single or a double bond that exists there. We know that it's something between a single and a double bond, which we now are calling a 1.5 bond, which is shorter than a single bond in length, but stronger than a single bond in strength. So the molecular orbital theory helps us explain why all of these bonds and their bond energies are actually the same, despite the fact that we sometimes depict it as a single bond or a multiple bond. So that's going to be what we've been terming 1.5 bond for every bond, and now we're going to explain some of the theory behind it. This is a little exciting because you're learning some really upper level chemistry, but don't get overwhelmed. It's going to be something that helps, we're going to pick out kind of the easy points that we should be able to know or be able to find from a molecular orbital diagram. So the delocalization of electrons is supposed to be explained through the molecular orbital theory and explain why diatomic molecules exist. Some species are able to be diatomic, whereas others are unlikely or will never be a diatomic molecule based on its stability. So here's the background. I know you just got really comfortable with the atomic orbitals and you're liking the hybridization model, but we're actually now transitioning to a non-atomic orbital system to a molecular orbital system, which is going to be molecular orbitals are orbitals that are the same across the entire molecule, and that's going to be where our electrons are now existing. They again, similar to the atomic orbital hybridization theory, they have definite shapes and energies that we've been associating with them. Again, just like any orbital, they're going to hold 2 electrons with opposite spins, so none of that's new at all. But now we're going to start to pull together how some of these orbitals can come together to form a bonding situation, also called a bonding orbital, where they also have this alter ego where the 2 orbitals can come together in a area where they're considered anti-bonding or non-bonding, because they are of higher energy. So a high energy state generally means that something's not going to exist there under stable conditions, so they are considered anti-bonding. They're not in phase. There's multiple ways to say this. So the molecular orbital theory, that's the bonding one, is the one that's of lower energy and has, if there are more electrons in the bonding orbitals, then the molecule will exist in that diatomic state. If there's a lack of bonding orbitals or bonding electrons in those orbitals compared to the anti-bonding ones, the molecule's of a high energy state, meaning it's unstable, and therefore we would say that the molecule would not form favorably. So generally what we do, just like normal, you're going to put electrons in the bonding orbitals first, or the lowest energy orbitals first, maximum 2 per orbital. Then we're going to consequently have to fill the anti-bonding orbitals with electrons after those bonding orbitals have been filled. So this is an example diagram first, and I have the diagrams drawn for you on each of the slides. This is supposed to be explaining why hydrogen gas can be diatomic. So what's coming into play here is that this is a hydrogen atom on the left and a hydrogen atom on the right. And the way they're shown is that they're coming together, so that they're coming to bond in a common area in the middle. Well, each of them bring their valence electrons. This is the 1s1 electron, and this is the 1s1 electron. So as they bring their electrons into the picture, here and here, these electrons are getting dumped into a lower energy system. Lower energy, you can see on the axis over here. That's a good thing. We want them to go into the lower energy system, which is a favorable situation. And from here, we actually will say, okay, that's it. There's no more electrons to be thrown into an orbital. The only orbital that is filled is the 1s, or the sigma orbital, which is in this case the bonding orbital. So there are two ways that orbitals can be depicted. This is a bonding situation where the overlap does occur. This is the anti-bonding situation where the two lobes or the two orbitals are not coming together in a phase, a similar phase, so they do not overlap, which would be a non-bonding situation. These don't bond. So really, we're going to see which is the higher number of electrons in the bonding versus anti-bonding, and that will help us figure out if something will form or not form in its atomic state. So what you're going to have to be able to do, according to the AP College Board, is that we're going to have to look at the molecular orbital diagrams and determine the bond order, which we've indicated before, is similar to saying a double bond, triple bond, which would be like second order and third order. Not exactly going to correlate all the time, but most of the time, you're going to predict the stability, meaning will it form or will it not form for a particular diatomic species. And so here is the actual calculation for the bond order. Write that down for yourself. The bond order is equal to half of the electrons in the bonding orbitals, which are the stable ones, minus half of the electrons in the anti-bonding orbitals. And that will give us a bond order. And so how are you going to know something is stable or not? If it's greater than 0, then it's going to be a stable, likely forming molecule or diatomic species. If it's less than 0 or equal to 0, it's considered not stable, not likely to form. Lastly, we'll look at the paramagnetic and the diamagnetic terminology again. And so if you have paired electrons all the way, 100% paired, so no unpaired, all paired electrons, then it just don't react to the magnetic field. And don't for me is diamagnetic. And that's how I've remembered it since I was a youngin'. And then the paramagnetic species do have a slightly polar nature to them. And so if they're polar in nature, they usually have one unpaired or more unpaired electrons, meaning there's a polarity that exists because there's no counter spin of the electron, so they will respond to the magnetic field. So para I always refer to as polar generally. Diamagnetic would be considered nonpolar. So let's go back and calculate the bond order of our previous example using this scheme here for calculation purposes. So here we have the bond order formula. Bond order is equal to half of the bonding orbitals minus the anti-bonding orbitals with the electrons in it. So if you count them, you're going to say 1/2 is equal to, or excuse me, bond order is equal to half of 2 electrons minus 0 electrons. So half of 2 minus 0 is 1. And you'll see that this exists as a single bond. What am I writing here? A single bonding situation. And that, in fact, is what we see between hydrogen and hydrogen in a diatomic species. So let's look a little bit more. The correlations you should make from the bond orbital and the strength is right here highlighted in yellow. So the higher or the larger the bond order that we calculate, that means we have a stronger bond. If we have a stronger bond, that's a shorter bond. I'm not sure what this is. Shorter bond and greater bond energy and usually greater stability. So those are the associations that you will make once you know the bond order. And so in our general case, you normally know what some of these diatomic molecules look like. We've drawn them for about 2 years now, I think, at this point. And so you know that diatomic nitrogen looks like this. And we are going to confirm that this is a third order system, or the bond order is equal to 3. And that's correlating to the fact that it is a triple bond. But you might have to look into some unusual cases. There's some great links here if you want some more information on this. Okay, so the orbitals are labeled a little funky. They're labeled as sigma, sigma star, or pi and pi star. And so that's what I've indicated for you. Knowing that the star indicates an excited, it's not really excited, it's a high energy state. Let's go with high energy instead of excited. And that's going to help you remember that it's an anti-bonding system, and you'll see the same thing on this star and this star. So these are going to be how we draw the molecular orbitals, and the pictures I think will make more sense once you see them. This terminology will make more sense once you see them. But the S sublevel is going to have 2 orbitals together, coming together, and the P orbitals is going to have a total of 6 orbitals coming together. But the orbitals are split into bonding and anti-bonding, and they're ordered in a specific manner, according again to Aufbau's principle of energy slowly increasing as we go across these orbitals. So we're going to see this in a pictorial manner now. Oh, one more thing before we go. This is, again, another way to indicate that something is in phase or out of phase, or this would be considered bonding because there's some overlap here in the molecular orbitals, and this would be considered anti-bonding. And so we're going to try to deal with mainly S and P orbitals. The S orbitals are really easy to see, the bonding and anti-bonding. The constructive and destructive is another term for that. The P level orbitals are a little bit more complicated, as you can see in some of these pictures. Just try to indicate that something is bonding or anti-bonding. So you can see that these are bonding, these are anti-bonding because they're not overlapping, or these are bonding because you can see the overlap here and here, and these are anti-bonding because they're not. So you can see the system of organization here, but these are not ones we're really going to focus on drawing. I just wanted to show you what they would look like. So let's start off with the easy one. And so this is actually the same example as we did earlier with the hydrogen. Again, let's just kind of work through these one by one for the homogeneous systems, where they have the 2 elements coming together that are the same element. So this is the hydrogen atom 1 with its 1s electron. So this is atom 1. This is the second atom of hydrogen with this 1s electron because of the 1s1 electron configuration of its valence shell. So what's going to do is going to dump those electrons into the lower bonding orbital here. We call this sigma 1s because this is the 1s orbital, that's a molecular orbital that's being filled, and that's it. This is the sigma star 1s, and there's 0 in there. So calculate the bond order by taking 1/2 of bonding electrons, which would be 2, minus 0 for the anti-bonding electrons, because there are 0 here in the upper orbital. So our bond order is 1. So this is a stable system, and it will exist. Diatomic helium. So we're adding on 1 more electron, 1s2, 1s2. So this is the 1s orbital from helium atom, and this is another helium atom over here on the left with its 1s orbital containing 2 electrons. So we're going to have to fill from the bottom up. This is the sigma 1s orbital. This is the sigma star 1s orbital. And so we're going to dump these electrons in from bottom to top. 1 goes in here, and they counter each other with spin. And then another 2 go in the anti-bonding orbital system. And that's because we have a net total of 4 electrons that must be accounted for in our overall molecular orbital. So bond order, again, is equal to 1/2 bonding electrons minus anti-bonding electrons, or in this case, 2 minus 2. That would give us 0, which would indicate to you that diatomic helium probably is not going to exist. So not likely to exist because it's not a stable system. And then we've never seen diatomic helium, so that kind of confirms our belief there. Now we have a bigger diatomic system with 3 electrons in it. So this lithium atom over here has 3 electrons to take care of, which is a 1s2, 2s1 valence shell. So I'm actually going to have to add to our diagram, which you can see I actually have added here. This is the first energy level. This is the second energy level with our 1s electrons involved. So this is another 1s, 2s1 energy system, or electron system. So our first one, 1s and 1s with our 2 electrons in it. I think the inner shells are very easy to recognize because the inner shells, all of them get filled up. So the sigma 1s and sigma star 1s orbitals get 100% filled with electrons countering spins. It's our 2s orbitals where we only have one electron in each of them, and I've drawn them opposite. You could draw them the same spin though. Have it. You're going to send these electrons down to a lower energy bonding orbital called the sigma 2s because it's the 2s orbitals. And this would be considered the sigma star 2s. And so these electrons from lithium's valence shell are going to get piled into the sigma 2s orbital, leaving none available for the antibonding orbitals. So let's see here how the bond order works out for lithium, diatomic lithium. So bond order is equal to 1/2. Bonding electrons, I'm going to circle those in red here. Bonding, so that's 4 electrons here, minus the antibonding orbitals, which I'll circle in green, being 2 and 0, so that's just 2 electrons. So we have 1/2 of 2, which is 1. So technically, diatomic lithium can exist. It's okay to exist because it's a stable system, because the bond order is greater than 1. We just don't often see that. Next, we have diatomic beryllium. Similar situation. 1s orbitals, so beryllium is 1s2, 2s2, as it's a number of electrons being 4. So I'm going to quickly fill our 1s, or first energy level. So 1s, 2 electrons go into the bonding orbital 1s, so sigma 1s, and then sigma star 1s also gets 2 electrons from our 2 atoms of beryllium coming together. Then we have the 2s energy levels with their 2 electrons in it, and so they're going to get funneled down to the sigma 2s orbital, 1 up and 1 down, and then the sigma star 2s orbital with 1 up and 1 down. So this is a full shell all the way, full orbitals bonding and anti-bonding. So bond order here is equal to 1/2 of bonding orbitals, which I'll do in blue. Bonding and bonding orbitals, that's 4, minus the anti-bondings here in red, 2, 4, so that's 4. So our bond order is 0. Beryllium diatomic will not exist in nature. It's not stable. Now we're getting to some interesting ones because we have p orbitals to consider. The p orbitals where our p electrons exist in boron, for example, are going to be considered in our full example. But they're here at the top. I'm going to scroll down to show you from our starting system of the first energy level, the second energy level. So this is the 1s2, this is the 2s2, and boron, being 1 into p block, has 2p1 to include in the upper molecular orbital. So we're going to do this really quickly again. 1s2, they get funneled into the sigma 1s, and then the sigma star 1s. So we quickly see that all 4 of those get filled, and then the 2s, 2s2 electrons, sigma 2s, sigma star 2s. Again, those quickly all get filled. Now we have to deal with the 2p electrons. So this is the 2p sublevel, and this is the 2p sublevel from each of the borons coming together. Each of them only have 1 electron in those. They will get shuffled down to the lowest energy orbitals, which are actually the pi 2p. This is the first time we've seen this, pi 2p. And I'll label the others for you just so you know what they are. This is sigma 2p, and then above that we have pi star 2p, an antibonding orbital, and then sigma star 2p, 2s, excuse me. Nope, lies, that was 2p, I was right. Sigma star 2p, the other antibonding orbital. So since we only have 2 electrons, they are going to go into these 2 orbitals one at a time, and I'm going to do them as opposite spins just to give you something different. But they are in the bonding p orbitals. So, bond order for boron, diatomic boron. Bond order is 1/2 of the bonding electrons. So I'm going to scroll back down to the bottom. Bonding electrons, we have 2, 4, 6. So that's 6 bonding electrons minus the 2, 4, 0. So there's nothing in the p level orbitals. So that's 2, 4. So 6 minus 4 is 2, divided by 2 is 1. That means it can exist because it has a bond order greater than 0. Okay, so I'm going to go ahead and move on to nitrogen, and then I'll do an oxygen one. And there are more for you to practice as needed. So diatomic nitrogen. Quickly, again, we can do the entire system as a whole, where we have 1s2, 2s2, and then 2p3 electrons from each of the nitrogen atoms coming together. Remember, there's one on the left and one on the right. So we'll quickly go through 1s2 and push those into the sigma 1s, sigma star 1s, 2s2, push them into the sigma 2s and sigma star 2s, and just filling them up from bottom, low energy. Remember, this is low energy to high energy. And then our 2p electrons, there are 3, 1, 2, 3, and then the 2p3 electrons, 1, 2, 3. So your job is to understand that they go from the lowest energy level to the highest, meaning we have 6 total electrons that have to go into these boxes. This again is the 2 pi 2p orbital. This is the sigma 2p orbital. This is the pi star 2p orbital. And this is the sigma star 2p orbital. Those are the antibonding ones at the top because they're high energy. So we're going to go 1, 2, 3, 4, 5, 6. So we have 6 electrons in these bonding orbitals here. So if you go back, pause for a second, and try to count up your bonding versus antibonding electrons, you'll find your bond order. Bond order is half of the bonding. So I'm going to scroll down real fast. We have 2, 4, 6, 8, 10. 10 electrons in our bonding orbitals, minus, and I'll do this one in red for you, the couple, start at the bottom, 2, 4, 0, because there's none in the p orbitals, 4 antibonding, so that gives us 10 minus 4 is 6, divided by 2 is 3. That should show you that the bond order is 3, which is stable, first of all, incredibly stable. It's a really short bond. It's a triple bond in this case, which you're like, duh, I knew that. Nitrogen triple bonds. It's a very strong bond, and it has a high bond energy, which is the energy required to break that triple bond, endothermic process. Okay, so once we go from boron, boron, carbon, and nitrogen, and we go over to oxygen, fluorine, and neon, we're going to see a slight rearrangement of these molecular orbitals because now we have a 4th, 5th, and 6th p electron. So the order of the molecular orbital stability slightly changes. So we'll see that here. Notice that, or this is the top of oxygen, by the way. So I've got the bottom. This is the 1s, 2s, and 2p. So with oxygen, we now have our pi orbitals for the 2p only having 1 orbital, and the sigma 2p having 2 orbitals. Again, the pi 2p antibonding, because of the electron-electron repulsion, by the way, 2p, so pi star 2p at the 3rd level, and then the sigma star 2p at the upper level. That's the only difference here. So pause this, try to fill out oxygens, and then I will do this one for you. Okay, hope that you pause that one for a moment. Starting at the bottom, we're going to go ahead and do 1s for oxygen. So 1s, 2 electrons get filled into the sigma 1s and sigma star 1s. The 2s electrons get filled into the sigma 2s and sigma star 2s. 1, 2, 1, 2. So everybody's full up to here. Then we have in oxygen 2p4. And so we have 2p, 1, 2, 3, 4. And this again over here is 2p, 1, 2, 3, 4, which is going to create a system where we need to put 8 total electrons in the molecular orbitals. So starting from my box system I have set up for you, from the pi to p, we put 2 electrons here, counter to each other, and then 1, 1, 2, 2 into the sigma 2p. So far, that's only 8 electrons, and those 6 electrons. So then the 2 more have to go into 2 separate pi star 2p orbitals, and I want you to just recognize right here that these are unpaired. So far, basically everything we've drawn outside of boron has been paired up 100%. So because this is unpaired, I want you to think about, is that paramagnetic or diamagnetic? Since it's unpaired, this is going to be considered polar because nobody's countering the upward spin. So this is paramagnetic. Paramagnetic means it will respond to a magnetic field. Okay, now we're done with that fun fact. Let's do the bond order. Bond order for oxygen is 1/2 of the 10 bonding, so 2, 4, 6, 8, 10, 10 bonding, minus the anti-bonding of 2, 4, 6, because there's only 2 there. So that's 6 electrons in the anti-bonding. 10 minus 6 is 4, divided by 2 is 2. Guess what, guys? That's going to exist, and it's going to exist in a double bonding situation. And that double bond is weaker and longer than a triple bond. All right, so I hope that you can actually fulfill the rest of these diatomic molecules, predict the stability, the bond order, and understand a little bit more about the evolution of theories and why we have theories. Theories always have help us explain experimental evidence that we cannot explain with our current theory. Therefore, as good scientists, we must find ways to further our explanations. You guys have your problem sets to work on. Thank you.